Hi everyone, this is Kalyan Kumar and welcome once again to Chemistry Universe. In the last video number 3, we did aromatic molecules. We found out what are aromatic molecules, what are non-aromatic molecules, what are anti-aromatic molecules. And as I mentioned in the last video, this one is a look at the molecular orbital theory approach to aromatic molecules. And again, as I had mentioned before, this is not something which is very much required for your grade 12 course, or even if you're preparing for an entrance exam. I don't think this would be that much important for it. But if you want to learn, if you want to explore, if you really want to understand how things work in the space of molecular orbital theory, this will be a good video for you. So let's begin. Aromaticity with the molecular orbital approach. So molecular orbital theory for aromatic molecules, and we are going to begin by emphasizing the unique properties of benzene. The molecular orbital theory is especially helpful in explaining the unique properties of aromatic compounds such as benzene. And this, as you can see, is benzene. Now, although benzene is most often drawn with 3 double bonds and 3 single bonds, in fact, all of the carbon-carbon bonds are exactly the same length, which is 138 picometers. In addition, the pi bonds in benzene are significantly less reactive than the normal pi bonds, which are both isolated and conjugated. So, if you take a straight chain, obviously if it is a straight chain, it's not going to be aromatic, and double bonds in them, irrespective of whether they are isolated, that means they are not conjugated, or even if you take conjugated, the double bonds of benzene behave even more uniquely than these. They are less reactive than these pi bonds. Something about the structure of benzene makes its pi bonding arrangement especially stable, and this something has a name, and that is what we described as aromaticity. But what exactly is this aromaticity property that makes these pi bonds unique and so stable? In large part, the answer to this question lies in the fact that benzene is a cyclic molecule in which all of the ring atoms are sp2 hybridized. This allows the pi electrons to be delocalized in molecular orbitals that extend all the way around the ring above and below the plane. So the fact of the matter is that if I were to take 135 hexatriene and remove the corner hydrogens and join them, we get benzene. And just by doing that, what happens is the pi electrons which were flowing above and below the plane of the molecule in a linear fashion, now the moment I join the 2 carbon atoms, now they are in a cyclic electronic cloud. This is what brings out this nature in it, which we call as aromaticity. Now, for this to happen, of course, the ring must be planar, otherwise the p orbitals couldn't overlap properly, and benzene is indeed known to be a flat molecule. We discussed most of these in aromaticity. See, in aromaticity, we talked about how to identify that. What are the rules here? Here we are going to understand why are those rules. What is so special about 4n plus 2? What is so special about 4n for making something anti-aromatic? So, if I were to give you an image of benzene, this is how it looks like. Remember, the plus and the minus are exhibited by the blue and the red. You can take anything to be the plus and anything to be the minus. And remember, these are wave functions. The minus doesn't mean anything special, or the plus doesn't mean anything special. Above the axis, below the axis, that's all. And the pi electron delocalized around the ring, both above and below the plane. Now, do all cyclic molecules with alternating single and double bonds have this aromatic stability? And we've already discussed this in the previous video. The answer, in fact, is no. Because some are anti-aromatic, some are not even both. If you remember the 8-membered ring, cyclooctatetraene, the ring is not flat and its pi bonds react like normal alkenes. In fact, even had it been flat, it would have been anti-aromatic, which is the very reason why it went out of plane. It looks somewhat like this. Clearly, it takes something more to be aromatic than just a ring and with alternate pi bonds. And this can best be explained with the molecular orbital theory. Let's look at an energy diagram of the pi molecular orbitals in hexa 135 triene and benzene. So remember, I'm first going to use hexa 135 triene and I'm numbering the carbons like this. And this is my energy axis going up. And these are the atomic orbitals of the 6 carbon atoms. Remember, these are the p orbitals. I'm only looking at the p, not the sigma. So when you look at the p, you have 1 electron in each of the p orbitals. And now, when they interact, their wave functions interact, this is what we get. These are atomic orbitals and this is the energy level of the atomic orbitals. Now we get a molecular orbital which is lowest in energy. We call it psi 1 and this is how it looks like if I were to give you a visual image. But remember, all these are mathematical additions, mathematical multiplications. These are not exactly the picture, but this is how you will be able to understand them better. Now if you notice here, there's a bonding interaction here, blue-blue, blue-blue, second bonding interaction, another blue-blue, third bonding interaction, fourth bonding interaction and fifth bonding interaction. So there are 5 bonding interactions and as you can see, the blue and the red never meet. So there are 0 nodes. Nodes are the places where the probability of finding the electron is virtually 0. And there are no anti-bonding interactions. As you can see, blue and red don't meet. So this is 0 nodes, 5 bonding interactions, 0 anti-bonding interactions. That effectively makes it 5 bonding, which is why we call it a bonding MO. The bonding MO and the anti-bonding MO are distinguished by the fact that the net bonding in it should be a bonding. And if the net is anti-bonding, it will be called an anti-bonding orbital. So the next one, psi 2, well, this is how you can imagine that. As you can see, this is the place where the blue and the red interact. And therefore they don't interact. There is a node here. So we call this as a nodal plane or a node. And so how many bonding do you find? 1, 2, 3, 4. Remember, even these are bonding because red and the blue are just the signs. So bonding 1, bonding 2, bonding 3, bonding 4. 4 bonding, and here you find an anti-bonding and 1 node. So 1 node, 4 bonding, 1 anti-bonding, and the net is 3 bonding, which is why it's called bonding MO. Now let's look at psi 3. This looks like this. Bonding 1, bonding 2, bonding 3. How many nodes? 2 of them. And these are anti-bonding interactions as well. So 3 bonding and 2 anti-bonding, effectively I still get 1 bonding. So that's why we call it a bonding MO. 2 nodes, 3 bonding interactions, 2 anti-bonding and 1 bonding is the net value. Let's look at the anti-bonding. Here of course the net will be anti-bonding. Now another thing you might feel is that isn't the number of nodes equal to the number of anti-bonding interactions? So far it is coming out to be true. In fact, in a linear thing like this, they will always be true, but not in a cyclic thing. In the cyclic thing, the nodes will be different from the anti-bonding, or may be different rather. So now let's look at the first of the anti-bonding. Psi 4 star, star represents anti-bonding. This looks like this. Now remember, I'm not going to explain to you how we got this. This is based on mathematical calculation and this is a visual representation of the mathematical values that we get. So how many bonding do you notice? Can you notice 2 bonding? 1, 2. How many anti-bonding? 1, 2, 3. So anti-bonding wins. That's why it's anti-bonding. So I got 3 nodes and 3 anti-bonding interactions and only 2 bonding, 3 nodes, 2 bonding, 3 anti-bonding and 1 anti-bonding, which is why it's anti-bonding net. The next one, psi 5 star. Remember, the number of molecular orbitals will be equal to the number of atomic orbitals from which they are formed. This you must have done in chemical bonding. And here you see the image. Can you see antibonding 1, antibonding 2, antibonding 3, antibonding 4 and only 1 bonding. So effectively 3 antibonding. So effectively 3 antibonding. And the top one, the highest in energy, all of it is antibonding. There is no bonding at all. And how many antibonding nodes do you find? 1, 2, 3, 4, 5 antibonding, 0 bonding, highest in energy. Now, another thing that we need to understand here is, now let's put the electrons. So how do you think we are going to put the electrons? The electrons are 6 in number. And remember, we have to follow the F-bow principle and the Hund's rule. So, and of course the Hund's rule won't work here because there is nothing degenerate. So 2 electrons will go to Psi1, 2 will go to Psi2, and 2 will go to Psi3, which is why this molecule becomes stable, because all the electrons are paired. They look like a noble gas configuration here, and you find that all these electrons are paired, and therefore this molecule is perfectly stable. And you also notice that, remember, between 2 and 3, between carbon 2 and 3, there is bonding here. There is bonding here also between 2 and 3, which is why we talk about resonance. We say this bond has partial pi bond character. Now, Psi3 is the highest orbital which is occupied. Psi4 star is the lowest orbital in energy which is unoccupied. So, Psi3 is the highest occupied molecular orbital called the HOMO, and Psi4 star is the lowest unoccupied molecular orbital called the LUMO. Now let's look at benzene now. The similar treatment for benzene, things are going to be much different here. Again, energy axis, 6 orbitals, 6 carbons, the p electrons, and this is the energy of the atomic orbitals. Now let's check. First, Psi1, this is how it looks like. Now can you see the bonding interactions have increased? 1, 2, 3, 4, 5, 6. If you remember the previous one, we only had 5. Let's check that also. Yeah. Now if you look at this again, you see 5 bonding, right? There was no node, but there was 5 bonding. But now look at this. Can you notice 6 bonding? So can you see the bondings have increased? Which means this Psi1 is definitely going to be lower than the Psi1 there. Now let's look at the next higher one. Now these are 2 degenerates, Psi2 and Psi3. And how do they look like? Mathematical calculations suggest this as well as this. Now what this dot basically means is that these p orbitals are not contributing anything. So they've just vanished. Again, remember, visual representation of mathematical calculations. So here how many bonding do you have? 1 bonding, 2 bonding, 3 bonding, 4 bonding, 1 antibonding and 1 antibonding, 2 antibonding and 4 bonding. But can you see there is only 1 nodal plane here? So if you look at nodal plane, you get only 1. Here nodal plane is only 1. And here 2 bonding, bonding 1, bonding 2, and this is the nodal plane. And as you can see, there is 1 node, 2 bonding, but here can you see node is 1, but can you see there is no antibonding here? Blue and red are never together. Here blue and red are together. So bondings are 2 plus 2, 4. Antibondings are 2, that makes it net 2 bonding. Here bondings are 2, but antibonding is 0, though node is 1. So this is where the nodes and antibonding interactions differ. So in the previous case, 1 node, 4 bonding, 2 antibonding, that makes it 2 bonding. In the second one, there is 1 node, 2 bonding, and there is 0 antibonding, that makes it net again 2 bonding, which is why they are degenerate. The total bonding interactions net are equal. Now let's go for the higher ones. These two are also degenerate. Psi4 star, Psi5 star. And how do they look like? One of them looks like this the other looks like this. How many bonding do you see? 1, 2. How many anti-bonding do you see? 1, 2, 3, 4. So can you see net is 2 anti-bonding? Look at this. Anti-bonding 1, anti-bonding 2. Again net 2 anti-bonding. No bonding here. So what do we perceive? The net 2 anti-bonding in both, which is why they are degenerate. Now if you want to look at the nodes, obviously there's one nodal plane like this, one nodal plane like this, because in anti-bonding interactions, you will not find any electrons. And here there's one nodal plane like this, one like this. So here the nodal planes are 2. In the first one, there are 2 bonding interactions and 4 anti-bonding. That gives you net 2 anti-bonding. In the next one, you got 2 nodes and 0 bonding and 2 anti-bonding, again giving you net 2 anti-bonding. And now let's look at the most unstable, the highest in energy. Here, you find absolutely no bonding. There are 6 anti-bonding interactions. And the nodal planes are 3. So 3 nodes, 0 bonding, 6 anti-bonding, net is 6 anti-bond. So how am I going to fill up the electrons? Well, obviously follow the F-bar principle, 2 here. And now follow Hund's rule. But since all of them are paired, well, Psi2 and Psi3 get filled. So what makes this more stable? Can you understand that here the number of bonding is 2. Okay? Here the number of bonding is 6. So obviously this makes the system so much stable that in the previous case, in the straight chain, remember this was actually 3 bonding. But this makes the system so stable by bringing it down that it net becomes more stable than the linear chain. And remember, in the previous case, there were only 2 electrons in Psi2, whereas Psi3 was above this, having only 1 bonding interaction. Look at this one. Just check this out. The second one had 3 bonding net, but the top one had only 1 bonding. Whereas now, we have a different situation. Here both of them have 2 bonding. That also results in decrease of energy. And that helps to make the system more stable than the linear one. And again, Psi2 and Psi3 are the HOMO, and Psi4 star and Psi5 star are the LUMO. So this is how the bonding works in a 6-membered ring, and the explanation is here. The quantum mechanical calculations tell us that there are 6 pi molecular orbitals, and the result of the molecular orbital calculation tells us that the lowest and the highest energies are these, and we follow the F-bar principle, and benzene gets a full set of bonding MOs, similar in many ways to full shell of electrons. But of course, even the linear one had full shell of electrons, but the energies of the MOs here are lower. Now let's look at one more, and this fellow is the anti-aromatic cyclobutadiene. Let's see how this works. In the cyclobutadiene, there's a square with 2 pi bonds. So there are 4. This is the energy axis. 4 p orbitals, 1 electron each. And these are atomic orbitals, and this is the energy. And the lowest is this, Psi1. This is the energy level. And how many bonding do you find? Bonding 1, bonding 2, bonding 3, bonding 4. 4 bonding, 0 antibonding, net is 4 bonding. No node here. But then look at these two, Psi2 and Psi3. Can you see bonding 1, bonding 2, antibonding 1, antibonding 2. Can you see they cancel out? Can you see this is net 0 bonding and 0 antibonding? Here 0 bonding, no antibonding, again it is 0. This is the nodal plane. So these are 0 bonding and 0 antibonding, which means that their energy will be almost equal to the level of atomic orbitals, because they are net neither bonding nor antibonding, and these are the two levels. And the highest one, of course, is all over antibonding. There are 1, 2, 3, 4 antibonding interactions, and I got this here. And the 4 electrons, how you are going to put them? You're going to put 2 here and 1 here and 1 here. So therefore, the electrons are first of all unpaired. That makes them reactive. At the same time, these are equal to the energy of atomic orbitals. They're not lower than that. They're definitely going to be less stable than aromatic as well as non-aromatic, in which all electrons were in bonding. So the result of molecular orbital calculation tells us that the lowest and highest are Psi1 and Psi4 star as shown. And notice that Psi2 and Psi3 are at the same energy level as the isolated 2pz atomic orbitals. These are therefore neither bonding nor anti-bonding, and they are called non-bonding MOs. Filling up the MOs with 4 pi electrons, we find that the last 2 would be unpaired and will go into the non-bonding. And because we don't have a perfect filled shell, this is not aromatic. And the electrons being unpaired, the molecule is anti-aromatic, and all aromatic are diamagnetic and the antis are paramagnetic. So that is the end of this video. I hope you got a little bit of a good idea how the molecular orbital theory helps you in understanding why anti-aromatic molecules are less stable than the aromatic, or for that matter the non-aromatic molecules. Of course, we can't really figure out why they use the word anti-aromatic. If one was aromatic, you could have had less aromatic or something, but I guess they chose the word anti-aromatic. But the anti has got nothing to do with anti-bonding orbitals. So it's not that in anti-aromatic the electrons go up to the anti-bonding. In some of them they do, but not in all of them, as you saw in cyclobutadiene. But anyway, I hope this video helps you in creating more interest in looking at a molecule in a slightly different way than simply following the rules. The next video that I'm going to do is called Frost Circles, and that will help you get the molecular orbital's energy without doing mathematical calculation. Now remember, here the ones that I showed you, the energy levels, 1 at the bottom, 2 degenerate, some of them were equal to the atomic, and in one case in benzene they were below the atomic, in antibonding they were equal to atomic. So how do we get these energy levels? There is a way of doing that with Frost circles. So that will be the next video. Again, remember, that is not a very essential video for you to see for your course, but if you're interested, you can get the molecular orbitals of a single ring system with alternate pi bonds using even the Frost circle. So with that, this is Kalyan Kumar saying goodbye, have a great day, and let's see you in the next video.